Have you ever walked into a beautifully designed space, maybe a restaurant with incredible atmosphere or really sleek office, or even just a perfectly laid out kitchen, and you just felt this sense of ease, like things just worked?
Hmm.
Beyond the paint colors or the furniture, there's this kind of underlying structure, almost like a quiet language of engineering and art that makes the space, well, breathe.
That's absolutely right. We usually admire the finished product,
Hmm.
the seamless look.
Yeah.
But the real genius, the sort of magic, it really lies in those unseen decisions, the choices made, and the meticulous execution of all the details. It's where that big design vision crashes into the hard realities of construction.
Precisely. And today we're taking a deep dive into the very fabric of our built environment, these unsung heroes of design and construction that really shape the spaces we live and work in.
Yeah, the stuff behind the walls.
Exactly. We're going to unpack the incredible world of interior detailing and construction from the ground up, quite literally, right up to the roofs over our heads. And our mission for you, listening in, is to give you a kind of shortcut to being truly well-informed about how buildings are actually put together, to help you understand the choices and also the constraints that go into every single component.
So you can really appreciate the thought behind it all.
Yeah, that detailed thought behind every wall, every door, floor, ceiling, and even, the often overlooked art of how it's all budgeted and costed out.
And for this deep dive, we've brought together a really comprehensive collection of documents. Architectural plans, interior design spec,
That big stack of stuff.
the big stack, yeah. It covers a huge range of topics, from the sort of core principles of detailing to specific construction methods for, well, pretty much everything. Walls, floors, you name it. And even a crucial look into cost estimation.
That sounds like a lot.
It is a lot of information, absolutely. But we're here to be your guides, Break it down piece by piece, reveal some of the hidden complexities, and hopefully some surprising insights along the way.
Okay, let's unpack this then. When we hear detailing, our minds might jump straight to technical drawings, maybe tiny, intricate, decorative bits. But what our research really shows is something, well, much deeper than that.
Yeah, what's truly fascinating here is that detailing isn't just a technical task. It's fundamentally a creative process.
Yeah.
It's all about problem solving.
Okay.
Think of it like the bridge, connecting the grand vision of an architect or designer with the actual physical reality of a finished building.
Right.
So you might have this sweeping concept, say, for a minimalist living room. Everything's seamless, hidden storage.
Mm-hmm.
Detailing is where you figure out how to actually achieve that. It means dealing with real-world constraints, making super precise choices about materials, how they connect, their finishes. It really blends the art side with the rigor of engineering.
So it's literally fitting the pieces together. Yeah.
Exactly. Fitting the pieces together, not just physically connecting things, but also visually aligning them. So every single element, from a door frame to a cabinet edge, it all contributes to this coherent, functional, and beautiful whole. It's like the hidden choreography that makes a space really sing.
Okay, so if detailing is this creative problem-solving thing, what does that actually mean for the final space we experience? Why should we, as listeners who maybe aren't building pros, why should we care about these seemingly tiny details?
Well, these details might look small on a blueprint, but their impact is, honestly, monumental. Detailing plays a few really key roles.
Yeah.
First, and maybe most importantly, it directly solves functional problems.
Right.
It responds to the specific needs that interior space is trying to meet. Take a door, for example.
Okay.
The tiny detail in how the door jamb meets the wall, how the hinges are perfectly set, how the strike plate lines up just right. It's not just about looking neat. It's about making sure that door opens and closes smoothly, without sticking or creaking, that it latches securely every single time, and that it actually provides the privacy or the sound insulation it's supposed to.
So without that detail, the beautiful door might just not work right. It might stick or let drafts in.
Exactly. It could be a source of constant frustration instead of a seamless interaction. And, beyond the purely practical stuff, detailing is also one of the most powerful ways to enhance the overall design intent of a project.
Okay, this is where the creativity comes in.
This is where it really shines. Those basic elements of design lines, rhythm, texture, form, and the bigger design concepts, like minimalism or industrial chic or maybe a rustic farmhouse feel. They're all reinforced and brought to life through how these smaller scale details are designed. A really sleek flush door detail, for instance. It just quietly reinforces that minimalist look, almost vanishing into the wall.
Right.
But maybe a big, chunky, exposed hinge or a raw, unfinished edge. That contributes massively to an industrial or rustic vibe. These are the things that, even if you don't consciously notice them all the time, they profoundly shape the comfort, the usability, and the whole aesthetic appeal of a room. They create that sort of aha feeling you get when you walk into a really well-designed space.
It's like the silent language of the building.
Precisely. It's the designer's intent communicated quietly.
That makes perfect sense. These details really are the hidden language. And speaking of foundational elements, let's talk walls. They're everywhere, seem so simple, but they're far from monolithic, are they?
Not at all.
Our sources highlight three main construction methods, and each one has its own character, its own implications for the space.
Indeed. We're mostly talking about drywall, concrete hollow block, or CHB walls, as they're often called, and wooden construction walls. And these aren't just random choices. They're fundamental elements. They influence everything built on top of them: structure, sound insulation, even the kinds of finishes you can put on.
Right, each one tells a different story.
Exactly. A different story about how that building is put together.
Okay, let's start with drywall. It's just incredibly common, right? Modern homes, offices. For someone who sees these smooth, painted surfaces everywhere, what's actually going on behind that paint? How's it built?
Right. Drywall construction, usually using light metal frames and boards. It's popular for a reason. It's versatile. It's efficient. The framing is mostly standardized, galvanized, iron GI metal studs.
Okay.
Those form the vertical skeleton of the wall, and they're typically anchored into matching GI metal tracks that run along the floor and ceiling. The beauty is in the standardization. These parts are designed to lock together perfectly, creating a frame that's sturdy but also pretty lightweight.
And the spacing of those frames, is that standard too?
Generally, yes. The frames are typically spaced at 60 centimeters on center.
Okay, 60 centimeter.
And that's not arbitrary. It's an engineering choice. It lines up perfectly with standard drywall board sizes, which are usually big sheets, like 4 feet by 8 feet.
Okay.
That consistent spacing is really crucial for supporting the boards properly, so they don't sag or get weak spots. Get that wrong, and your wall could, well, ripple or even crack later on.
Right. And the boards themselves?
The boards themselves are most commonly either 12mm gypsum board. People like it for its smooth finish, easy to paint, or maybe 6mm fiber cement board. That one offers better moisture and impact resistance, so you often see it in places like bathrooms.
Makes sense.
And once those boards are screwed onto the frame, there's a really key step for getting that seamless look we expect. That's the finishing.
Right, the taping and mudding.
Essentially, yeah. Applying a compound called skim coat over all the board joints, the seams, and any nail or screw holes. This creates that perfectly smooth, unbroken surface that's ready for paint or wallpaper. So, yeah, next time you see a smooth drywall, just remember the precision that went into making it look so simple.
That's a great breakdown. It really shows how those small details add up. Now let's switch gears to something, well, much more traditional, much heavier. The concrete hollow block wall, CHB. Feels very different, right? More robust.
Absolutely. CHB walls are a real staple, especially for exterior walls or maybe interior partition walls where you need serious robustness, durability, maybe better sound insulation.
Right.
The main components are the concrete hollow blocks themselves, basically big hollow concrete bricks laid in rows or courses. These are then usually covered with about an inch-thick layer of plaster on both sides. That gives you the smooth finished surface.
And reinforcement.
Crucially, yes. Steel reinforcement, usually metal rods, gets integrated within the block cavities and the mortar joints as it's built. That steel provides essential structural strength, helping the wall resist forces.
How's it built? Just stacking blocks?
Well, it involves careful layout, making sure the blocks are properly bonded with mortar between each one. Then the plaster is applied meticulously to both sides. And there's an often overlooked but really vital structural element in CHB walls: stiffener columns.
Stiffener columns, what are those?
They're basically vertical reinforced concrete elements built right into the wall at regular intervals, or maybe at points where there's extra stress. They provide additional structural integrity, helping resist lateral forces like wind or, seismic activity.
Ah, okay. So comparing CHB to drywall, it's a totally different beast.
Oh yeah, much more durable, much better sound insulation, often chosen just for its sheer solidity. Think between apartments or for fire separation walls.
And our sources also briefly mention wooden construction walls, just noting they're another option.
Yes, exactly. Our materials just acknowledge wooden construction walls as another common method. We don't have the detailed specs here today, but it's important to remember it's a viable and historically significant way to build. People often choose it for the natural look. It's renewable, Good thermal properties, especially in houses, gives a totally different feel again.
Fascinating. So many ways to build just a simple wall, each with its own story. Okay, once we have walls, we need openings, doors. We walk through them constantly, barely give them a thought. But wow, our sources reveal just how much thinking goes into their design, their function,
Hmm.
even how they shape our interactions.
It's pretty amazing when you break it down, isn't it? Fundamentally, yeah, doors give us access inside to out, room to room. But from the outside, they're also really key compositional elements in how a building looks.
How so?
Well, the way they punctuate or divide up the exterior walls, it hugely affects the building's massing, its visual weight, the scale, how articulated the whole form feels. They often set the tone for what's inside.
So it's not just a hole in the wall, it's a statement. And a functional one, too. I guess an exterior door needs different things than an interior one.
Absolutely. Exterior doors, for example, they have to provide really good weather-tight seals when they're closed. Keep out rain, wind, and ideally they should match the thermal insulation value of the walls they're in, more or less. Prevent heat loss or gain.
Right, energy efficiency.
Exactly. Interior doors, on the other hand, the priority is usually visual and maybe acoustical privacy. Beyond that, all doors get looked at really closely. For ease of operation, do they swing easily, slide nicely?
Right.
Their durability, based on how often they'll be used, security features, and of course, how much light, ventilation, or view they might offer. And then there are building codes, especially for fire resistance, which is obviously crucial for safety and getting out in an emergency.
You also mentioned some specific door parts that often get missed but are actually important.
Yes, the materials make a useful distinction between a door saddle and a door threshold. A door saddle is usually that horizontal piece, often slightly raised, right at the bottom of the door frame, designed to shed water or mark a transition.
Okay.
A door threshold is a bit more general. It's the sill of the doorway. It could be part of the floor or a separate piece, often designed specifically to create a seal against the bottom of the door. So a saddle is a type of threshold, but not all thresholds are saddles. It's subtle, but important for weatherproofing and sometimes accessibility.
And the way a door opens, totally take that for granted, but there's a surprising number of ways, right? Each with different practical implications.
Oh, definitely. The operation type really dictates how the door interacts with the space around it. Affects traffic flow, furniture placement. The most common, obviously, is the swinging door.
Yeah.
Interior, exterior. You just need clear space for its arc.
Right. Don't put the sofa there.
Exactly. Then for tight spots, like closets, you often see bypass sliding doors. Two or more panels sliding past each other on parallel tracks saves floor space.
Mhm.
Then there's the surface sliding door, often called a barn door now.
Right.
Slides on a track mounted on the wall above the opening.
Mm-hmm.
Super popular aesthetically, right?
Yeah.
Can be interior or exterior, becomes a real design feature.
Yeah, you see those everywhere now.
And finally, folding doors. Accordion style. Great for saving space, and they can open up really large areas, creating a nice flow between rooms or maybe indoor-outdoor spaces.
What about the actual types of doors based on how they're made? The materials, I assume it's more than just wood or metal.
Our deep dive covers several key types. Hollow metal doors, very robust, often used in commercial or institutional places. Great durability, security, fire resistance.
Okay.
Then you have wood flesh doors. Smooth surface, no panels, very clean, contemporary look. Can be simple or have designs routed in.
Right.
Wood rail and style doors are more traditional. You have vertical styles. Horizontal rails, framing panels could be solid wood, glass, whatever. It gives you that classic, often paneled look. Glass doors are huge now, right? Maximize light, create that modern open feel. Can be frameless for a super minimalist look or framed in different materials for different levels of privacy or style.
And then there's the revolving door. Always feels so grand, almost like a moving sculpture.
Revolving doors are fascinating, a real blend of engineering and efficiency. Usually 3 or 4 leaves rotating around a central pivot inside a cylindrical vestibule. You see them mainly in big commercial or institutional buildings for very specific reasons.
Like what?
They provide a continuous weather seal, which means they basically eliminate drafts and they massively cut down on heating and cooling losses. Super energy efficient. Plus, they handle a ton of traffic, maybe up to 2,000 people per hour. Critical for busy places like hotels or airports.
Wow, okay. Beyond the door itself, there's all the hardware, the bits that make it work. I know from fixing doors at home, a good lock set or hinge makes a world of difference.
Oh, absolutely. The hardware is the unsung hero. Lock sets the whole assembly with knobs or levers, the decorative plates, sometimes called the rose,
The rose, okay.
and the locking mechanism inside. Crucial for security, privacy, and just how the door feels to use. Hinges, too, are fundamental. Most common are butt hinges, two plates, or leaves, joined by a pin, secured to the door and the jamb.
Right.
And how they're installed really changes the look. Some are fully recessed, so you only see the little knuckle when the door is closed, very clean. Others are surface mounted, making the hinge itself a visible design element. It's a subtle choice, big visual impact.
I never realized there were different ways to install hinges. What else is crucial for how doors function?
Well, door closers are pretty essential for heavy doors or doors used a lot, especially commercially. Hydraulic or pneumatic things that automatically close the door, nice and quiet. Prevents slamming, saves wear and tear on the frame and hardware.
Oh.
Panic hardware, critical safety item, usually on emergency exits. Less people push a bar to open the door quickly in an emergency, even if it's locked from outside.
Right, essential.
Weather stripping is vital for exterior doors and windows too. Flexible strips, metal, felt, vinyl, foam, rubber, placed strategically between the door or window and its frame. Creates a tight seal against rain, wind, reduces air and dust getting in. Big impact on energy efficiency and comfort. Needs to be durable, non-corrosive, ideally replaceable.
Makes sense.
And then there's other hardware mentioned. Push and pull bars for high-traffic doors, push and kick plates to protect the door surface, door stops, holders, bumpers to stop doors hitting walls, thresholds, we talked about those, and door tracks and guides for sliding and folding doors. Choosing the right door type, operation, and especially the hardware, it fundamentally changes how you experience a space. Privacy, light, safety, even the subconscious ways we interact with buildings every day.
Okay, once we've got access sorted with doors, we turn to bringing the outside and windows. Equally complex, maybe even more transformative for space, right?
Windows are definitely intricate. They do way more than just provide a view. Our sources show visuals of all the parts, sashes, frames, glazing this complex assembly, each piece designed for performance. And just like doors, windows have different operations. How they open dictates ventilation, interaction with inside and outside.
Tell us about those operations. I guess it's more than just open or close.
Oh yeah, lots of options. You've got fixed windows, don't open, just for light and view, framing that perfect landscape maybe. Casement windows are hinged at the side, swing outward. Great ventilation, clean look when open.
Okay.
Awning windows hinge at the top, swing out. Good, because you can have them open even in light rain. Hopper windows hinge at the bottom, swing in. Often see those in basements, maybe for privacy.
Right.
Sliding windows move horizontally on a track. Simple, space efficient, very common.
Yeah.
Double hung windows have two sashes that slide vertically past each other. Lets you ventilate from the top or bottom or both. Very versatile. Jalousie windows. Those have multiple parallel glass slats, open and close like blinds. Adjustable ventilation and light. And pivoting windows rotate on a central pivot, horizontal or vertical. Unique ventilation, sometimes easier to clean. Often in more contemporary designs.
And the materials for window frames, do they each have their own pros and cons, different uses?
Definitely. Our sources focus on three main ones, each with its own character. First, aluminum windows. Popular because they're relatively low cost, lightweight, naturally corrosion resistant, durable in many places. But aluminum is a great conductor of heat, so they absolutely need what's called a thermal break. Usually synthetic rubber or plastic strips built into the frame to stop heat flowing from the warm side to the cool side. Without that, you get major heat loss or gain condensation problems. Really impact energy efficiency. Finishes can be anodized, baked enamel, high-performance resins. Very durable.
So good for budget, modern look, but you need that thermal break. What about steel windows? They often look sleeker, more industrial.
Steel windows have different strengths. Steel frames are made from rolled steel sections. And because steel is stronger and more rigid than aluminum, the sections can be much thinner.
Thinner profiles.
Exactly. Gives you incredibly narrow sight lines, lets you have bigger panes of glass in the same opening. Big plus for minimalist designs. Steel also transfers heat less readily than aluminum, so steel frames usually don't need thermal breaks for good performance.
Okay.
The sections are usually welded for strength, then galvanized or treated, primed for painting. Or you can get high-performance baked enamel, urethane, even PVC finishes for extra durability.
That makes sense. Thinner frames, more glass, less worry about thermal breaks. And finally, wooden windows. Very different feel, much warmer look.
Yes, wooden windows.
Yeah.
People love them for that natural aesthetic, the warmth. And wood is actually a very effective thermal insulator naturally. The frames are thicker than metal, but give great thermal performance. Usually made from kiln-dried, clear, straight-grain wood, factory-treated with water-repellent preservative to stop rot. You can stain them to show the grain or paint them any color. And a clever modern solution is cladding.
Cladding.
Yeah, the exterior of the wood frame gets covered with vinyl or maybe acrylic-coated aluminum sections. Needs no painting on the outside, so you get the classic wood look inside, but low maintenance and durability outside.
Best of both worlds.
Pretty much.
Yeah.
So yeah, the choice of window type, the material, it hugely impacts not just the look and the light, but energy efficiency, ventilation, even sound insulation.
Yeah.
All part of the building's overall comfort and character.
That's incredibly detailed. Makes you realize how much engineering goes into just framing a view. Okay, when we think about moving between floors, stairs are usually the first thing, right? But designing them isn't just making steps. It's like guiding a journey, ensuring safety, defining the space's character.
That's a really good way to put it. Stairs, along with ramps, elevators, escalators, they provide that essential access between levels. Stairs and ramps are typically what you find in buildings maybe 3 stories or less.
Right.
Elevators and escalators become more common in buildings 4 floors or more, or in places with really high traffic like shopping centers where you need high capacity.
Mm-hmm.
The main goal of good stair design is to put the least amount of physical strain on people using them. Make going up and down as comfortable and safe as possible.
Right.
But at the same time, the stair itself is a powerful design element. It reinforces the character of the space, the building's structure.
What are they usually made of?
Commonly wood, steel, or concrete. Durable materials. And crucially, their design and construction absolutely must meet strict building codes and universal design requirements. Safety and accessibility for everyone.
Right.
So interior design projects might involve designing a brand new stair, or quite often remodeling an existing one, maybe to bring an older stair up to current codes or just give it a modern look.
Like any specialized area, stairs have their own language, don't they? All these specific terms, understanding them helps appreciate the complexity. Let's break down the key parts and terms.
Yeah, this is where the precision and that human-centered design really show up. Let's go through the main ones designers and builders use.
Okay.
First, a baluster. That's one of the vertical bits holding up the handrail. They're spaced really carefully, dictated by codes, specifically to stop people, especially kids, from falling through.
We're at the gaps.
Exactly. A guardrail is a sturdy rail on landings or open floor edges, again, to prevent falls between floors. A handrail is the continuous rail you actually grasp for support going up or down. Codes control its placement, height, even the shape to make it ergonomic and safe.
Mm-hmm.
Headroom is the minimum clear vertical distance from the edge, the nose of a tread up to anything overhead, so you don't bang your head. Absolutely. A landing is the flat platform at the start or end of the stair, or importantly, between stair runs.
Mm-hmm.
A place to rest, change direction safely. The newel is the main post at the very bottom or top of the stair, usually bigger, more decorative than the balusters.
Mm-hmm. Okay.
Nosing, that's the little bit of the tread that hangs over the riser below it. That slight lip, it guides your foot, stops you kicking the riser as you go up. Small detail, big impact on safety and comfort.
Never thought about that.
Yeah. Rise is the total vertical distance the stair covers, floor to floor.
Mm-hmm.
It's the sum of all the individual riser heights. And the riser is the vertical part between treads. The tread is the horizontal part you step on.
Okay. Rise and tread. Got it.
The run is the total horizontal depth of the stair, the sum of all the tread depths. A stringer, sometimes called a carriage, is the main structural support holding the treads and risers up. Can be exposed for an industrial look or hidden for something more finished. And finally, a winder. That's a wedge-shaped tread used to make a turn instead of using a flat landing. Mostly see those in houses where space is tight. Commercial codes often restrict them because the changing tread depth can be a safety issue.
Wow. So many specific terms for just steps. Really highlights the precision needed. And
Yeah.
speaking of layout, what are the common types or shapes of stairs? Each seems to have its own feel.
Yeah, the shape hugely impacts flow, efficiency, and the look of a space. The simplest is a straight run, single flight, no turns. Efficient, but needs a long space.
Right.
An L-shaped stair is a straight run with one turn, usually with a landing at the corner. Very common, fits well in corners, space efficient. A U-shaped stair has 2 parallel flights connected by a landing. Makes a U-turn, often used for higher climbs, can look quite dramatic. A winder stair, like we said, uses those wedge treads instead of a landing to turn, mainly for saving space in homes. Curved stairs go up in a continuous, graceful curve. Adds elegance, fluidity. And a spiral stair is super compact. Steps radiate from a central pole, takes up minimal floor space. Great for tight spots, though maybe less comfy for everyday use or moving furniture.
Okay, here's where the math meets the design, right? Making sure stairs aren't just pretty, but also safe and functional. Our sources even give a step-by-step calculation example. Fascinating how exact this has to be.
Oh, this mathematical precision is absolutely fundamental. It's about designing stairs that feel comfortable and safe for people to use, and critically making sure they meet those strict building codes. Let's just walk through the basic principle using a simplified example.
Okay.
First step is to assume a target riser height, often around 150 millimeters or 0.15 meters. It's generally a comfortable height for most people. Next, you calculate the total number of risers. You take the total floor-to-floor height and divide it by your target riser height. So say your floor height is 3.3 meters, and you want 0.15 meter risers. 3.30 divided by 0.15 gives you 22 risers.
22 razors.
And then you figure out the total number of treads. It's always the number of risers minus 1.
Always minus 1.
Always minus 1.
Oh.
So 22 risers means you need 21 treads. Makes sense, right? You take 22 steps up, but you only land on 21 flat surfaces to get to the next level.
Ah, yeah. Okay. I see that.
The next calculations then involved distributing these risers and treads across any landings if it's not a straight run, and figuring out the exact depth of each tread so it all fits within the available stairwell length. These calculations are critical because even tiny errors can make a stair feel awkward, unsafe, or fail code inspection, leading to expensive fixes. It's the difference between a pleasant walk-up and a potential trip hazard.
Incredibly precise, and it makes total sense why it's so critical. Comfort, safety, meeting those codes. Our sources also show examples of stairs built with different materials.
Yeah, they give visual examples of how stairs are built using wood, concrete, and steel. Each material brings its own structural properties, aesthetic options, construction methods. Wood gives warmth, concrete gives mass and durability. Steel allows for those slender modern designs. The choice always depends on the building's overall design, structural needs, and of course the budget.
Stairs aren't the only way up or down, especially when we think about accessibility.
Indeed, ramps are sloped pathways, inside or outside, providing accessible circulation between levels. They're crucial alternatives to stairs, making buildings usable for everyone: wheelchair users, people with mobility issues, folks with strollers, bikes, other wheeled things.
Right.
The absolute critical element of a ramp is its gradient, the slope, the steepness. It's defined as the relationship between its rise, the vertical height it covers, and its run, the horizontal length it takes to cover that height.
Okay.
Often expressed as a ratio, like 1.20. That means for every 1 unit you go up vertically, you need 20 units of horizontal length.
Why is that ratio so important?
Because if a ramp is too steep, it's difficult, maybe even unsafe for people to use, especially in a wheelchair. But if it's too shallow, it becomes really inefficient. It takes up way too much space to go up even a small height. It's all about finding that essential balance for accessible design, making spaces truly inclusive for everyone.
Okay, moving from vertical travel to the horizontal plane, the floor. It's not just something we walk on, is it? It's a critical structural piece holding up everything and everyone, transferring huge loads.
You're absolutely right. Floor systems are these horizontal planes doing several crucial jobs. First, yeah, they support loads, both live loads, that's people, furniture, movable stuff, and dead loads, which is just the weight of the floor construction itself.
Right.
Second, they have to transfer those loads horizontally across the space to beams, columns, or load-bearing walls. And in modern building, rigid floor planes often act as horizontal diaphragms.
Horizontal diaphragms.
Yeah, they act like really wide, thin beams themselves. It's crucial for transferring lateral forces, like from strong winds or earthquakes over to the building's shear walls. Provides critical stability, earthquake resistance. It's this complex, silent network of forces constantly at play under our feet.
Wow. A lot more complex than just a flat surface. What are the main types of floor systems that make all this happen?
Our sources detail 3 main types: steel, wood, and concrete, each with its own structural vibe and typical uses. Within steel systems, we look mainly at tubular frame flooring.
Okay.
This uses steel joists, often square tubes, spaced regularly, attached to concrete beams. Then plywood or fiber cement boards get screwed on top as a subfloor. The big plus here is it's lighter, quicker to install, easy to drill through for electrical or plumbing. Great for upper floor extensions where heavy concrete might be too much.
The downsides.
Yeah, it's generally only suited for lighter floor finishes, vinyl tiles, linoleum, that sort of thing, and maybe not as good at soundproofing compared to heavier systems.
Okay. And the other steel type?
Steel deck flooring. This uses high-performance galvanized steel sheets. They act as permanent formwork and structural reinforcement for a thin, concrete slab poured on top. The pros here are significant. It creates a lighter but incredibly durable composite structure. Installation is way faster because you need less temporary formwork. And the underside of the steel deck. Often you can just paint it and it becomes the ceiling, gives that cool industrial look. Plus, it's termite and fire resistant.
So steel offers speed and lighter weight, maybe with some trade-offs. What about wood floor systems? Seems like the more traditional way.
Wood floor systems are classic, yeah. They have specific parts designed for strength. You've got the sill plate, that timber base resting on the foundation. The girder, a big main beam supporting heavy loads. Floor joists are the parallel timber beams that actually hold up the floor loads, transferring them to girders and walls.
Right.
Above those, the subfloor is the first solid layer, giving a stable base for the finished flooring.
Hmm.
And blocking or bridging short boards fixed vertically between the joists to stiffen them up, stop them twisting, keeps the floor feeling solid. People like these systems for their warmth, natural look, and it's often easier to make changes later on.
And then the heavyweight champ, concrete floors, seems like the most robust option, especially for bigger buildings.
Generally, yes. The concrete floor system, often a suspended concrete slab,
Mm-hmm.
uses concrete beams as the main structural support, unlike joist systems. Building it involves using temporary formworks, pouring concrete and steel, reinforcing bars rebar inside for immense strength.
Mm.
And a tiny, critical detail here, often unseen, is concrete rebar spacers. Little pieces that make sure the steel rebar is perfectly positioned inside the concrete pour, maintains the right spacing, the right concrete thickness for strength, prevents cracking. Super important. Then the slab needs that 28-day curing time to reach full strength.
And there are different types of concrete slabs too, right? Not just one kind. Sounds like more engineered complexity.
It is, and it's an important distinction. Each type is optimized for different spans, different loads. A one-way slab is reinforced mainly in one direction, usually cast with parallel supporting beams, like a strong plank.
Okay.
A one-way joist slab, or rib slab, is cast with closely spaced, shallow concrete joists underneath.
Right.
Better for longer spans and heavier loads than a simple one-way slab. Lighter, but still strong.
Right.
Then there's the two-way slab and beam system, reinforced in two directions, supported by beams on all four sides. Very effective for median spans, heavy loads. Strength in both directions.
Mm-hmm.
The two-way waffle slab has ribs in two directions, creating that grid pattern underneath. Lets it carry even heavier loads and span longer distances. You see it in big, open-plan buildings sometimes.
Yeah.
The two-way flat plate is just a uniform thickness slab, reinforced in two directions, supported directly by columns, no beams. Big advantage, lower floor-to-floor heights, saves overall building height, practical for apartments, hotels. And finally, the two-way flat slab, basically a flat plate, but thickened around the columns where it rests. These thicker bits, drop panels, increase its shear strength right where it needs it most.
So many variables just in the floor itself really helps visualize that complex interplay of materials, structure, engineering, all allowing buildings to stand, support us, even resist earthquakes. Okay, once the structure's in, then comes the part we actually touch and see. The flooring finish. Not just about looks, right?
Definitely not. Looks
All
are
of.
huge, obviously, for that final layer.
Yeah.
But choosing flooring finishes has to be based on critical functional stuff, too. Directly impacts user experience, how long the building lasts. You got to consider its durability, how well it handles abrasion, dents, scuffs, especially in busy areas.
Right, high traffic.
Exactly.
Mhm.
Ease of maintenance, resistance to dirt, moisture, grease, staining. Foot comfort, how much resilience or give it has underfoot. Slip resistance vital, especially in wet areas like bathrooms, kitchens. Avoid slick materials there. And impact noise. Resilient soft or porous flooring can cushion footstep sounds, even reduce sound bouncing between floors. Makes for a quieter, comfier place.
Let's dig into some common finishes, starting with wood. What makes wood flooring so enduringly popular, and what are the options?
Wood flooring is loved for that warm, natural look, right? And it's a nice blend of comfort, resilience, durability. The finish applied is critical, though. It needs to boost durability, resistance to water, dirt, stains, but without hiding the wood's natural beauty.
Right.
Common clear finishes are things like polyurethane, varnish, penetrating sealers. Can be glossy or satin. Stains add color, but let the grain show through. Or you can wax or paint wood floors for different looks.
And the types of wood flooring?
Our sources detail several. Strip flooring, narrow wood strips, often graded for appearance. Best grades have fewer defects like knots. Blank flooring, wider boards, often starting around 8 inches wide, gives a grander, more traditional feel. Parquet flooring, inlaid wood, set in geometric patterns, very decorative, artisanal.
Mm-hmm.
Block flooring, factory-assembled tiles, usually glued down with mastic, quicker install. And engineered hardwood flooring. This is a modern thing. Multiple layers for stability, durability, topped with a real wood veneer, often impregnated with acrylic or sealed with urethane or vinyl. Very durable panels, installation varies, nailing, gluing, floating. Depends on the type.
And then the solid, durable world of tile and stone, often chosen for those heavy-duty areas, right? Wet areas.
Exactly. Tile and stone flooring known for being solid, durable, often low maintenance. Ceramic mosaic tiles are small units, natural clay or porcelain. Unglazed clay types have those nice muted earth colors, tactile feel. Quarry tiles and pavers are larger, unglazed units of heat-hardened clay, often used in more rustic industrial settings. Robust. Stone tile flooring gives you that solid, permanent, super durable surface with natural beauty. Examples include slate can be irregular shapes or cut squares, works for formal or informal. Marble takes a high polish, gives that formal elegance, luxury. Granite also polishes well, incredibly durable, often used in high-traffic commercial spots or kitchen counters because it resists scratches, stains.
Our sources even compare ceramic and porcelain tiles directly. That's helpful because they can look similar but perform
We
differently.
do, and it's a really important difference for where you use them. Ceramic tiles are relatively low cost, softer, easier to cut with a basic tile cutter, but they're more porous than porcelain,
Meaning.
meaning they absorb liquids more easily,
Hmm.
more prone to stains, moisture damage, usually need more frequent cleaning, sealing. Porcelain tiles, on the other hand, are made from higher-grade clays fired at much higher temperatures. Makes them way harder, denser, much less porous.
Ah, okay. Less porous is good for.
Ideal for bathrooms, outdoor areas, any surface getting lots of traffic and moisture. Kitchen floors, countertops. Superior durability, stain resistance.
And how are they installed?
Usually either thin set or thick set. Thin set uses a thin layer of adhesive to stick the tile to a stable base. Most common modern way. Thick set is used over floors that might move a bit or are uneven. The tile sits on a thicker mortar bed, which helps stop the tiles cracking if the base moves. Provides a more robust foundation.
And the stuff between the tiles?
That's grout. Used to fill the spaces, comes in tons of colors, can blend in with the tile or create a contrasting pattern, another design element.
It's clear choosing flooring is way more than just looks. It's about the whole life cycle, maintenance, comfort, durability. Okay, moving on to built-in elements. Cabinetry, kitchens, libraries, everywhere. But it's more than just a box with a door, isn't it? It's fundamental to function, organization.
It truly is. Cabinetry is a huge category, not just kitchen and bathroom cabinets.
Hmm.
Includes base and wall units,
Yeah.
yeah, but it's also shelving, built-in desks, mantles, room dividers, all sorts of specialized storage and display things tailored to a space.
How are they made? All custom.
Can be. They might be pre-built units, fully assembled at the factory, ready to install, or partially made in the factory, finished on site, or wholly custom built right there on site. Depends on the project, how much customization you need, the budget. Manufactured cabinets, stock or semi-custom, usually come in standard sizes and styles, listed in catalogs. Makes it easier for designers to plan with them, often with options for doors, drawers, details.
And the materials. Our sources really detail the options for making cabinets, each affecting the look, durability, cost.
Yeah, this is critical. Material choice dramatically impacts the look and the long-term performance.
Mhm.
Solid wood is classic, highly valued, like the Gemelina wood example. Natural beauty, strength can be refinished.
Right.
Veneer options like walnut veneer on plywood or MDF give you the look of expensive wood without the full cost. Lots of aesthetic possibilities. Common substrates backing the veneer are MDF or plywood for stability.
Okay.
Plywood, especially marine plywood, can be used on its own, maybe stained or painted like white duco. Known for stability, moisture resistance, marine grade, good strength to weight.
Mm.
MDF, medium density fiberboard, is used a lot, often painted, like that gray duco example.
Mhm.
Very stable, smooth, great for painted finishes because it's so uniform.
Right.
Laminate, like that ocean blue Formica on plywood.
Oh.
Huge range of colors, patterns, textures. Durable, cost-effective, easy to clean, can mimic other materials. And melamine, like acacia melamine board on particle board. Cost-effective, comes pre-finished. Good scratch and moisture resistance for many uses. The choice really affects the look, feel, longevity, maintenance, and the final price tag.
What about actually building them and installing them? How do these intricate pieces get put together and hung securely, especially those heavy wall cabinets?
For hanging cabinets, especially upper ones, the French cleat system is really popular, very secure. It uses these interlocking wood or metal cleats. One angled piece on the cabinet, a matching angled piece securely fixed to the wall.
Oh, okay.
When you lift the cabinet onto the wall cleat, they lock together perfectly.
Hmm.
Super strong, makes installation precise, often easier to get them level.
Clever.
Another important detail is edge banding. It's a thin strip, often PVC or wood veneer, applied to seal the exposed raw edges of panels like plywood or particle board. Partly for looks, gives a finished edge, but also protects the core from moisture, wear. extends the cabinet's life. Our sources also mention a cabinet door overlay guide. That's basically a visual reference used during install to make sure doors line up right. Spacing is consistent relative to the frame. Guarantees that uniform, pleasing look.
This seems like where the detailing really comes alive on paper, becomes the exact blueprint for construction. Must need an incredible amount of info.
Exactly. Cabinet drawings are these super detailed sketches and elevations. They don't just show the design. They meticulously guide the building and installation of everything: casework, trim, doors.
Oh.
They include precise material lists, exact dimensions, clear instructions, all the measurements.
What kinds of drawings?
Usually plan views, looking down, elevation views, front, side, back, sectional views to show how it's built inside, and any other specific details needed, plus material and hardware specs.
What kind of info is absolutely crucial for those drawings to be accurate, to avoid costly mistakes on site?
Oh, you need everything functional detailed. Exact sink size, precise appliance sizes, and the required clearances being off by even a quarter-inch can mean an appliance just won't fit.
Right, nightmare.
Totally. The specific fixture selection, a detailed power and lighting plan that works with the cabinets, and any specialty cabinet conclusions, knife drawers, pull-out garbage bins, plate racks, they all have specific dimensions, how they operate. Installation can be modular, putting pre-built units in, or custom-built on site, which needs even more detail in the drawings because every piece is made to fit that unique space.
There's even a checklist.
Yeah, our sources provide a comprehensive checklist for cabinetry detail. Really underscores the precision needed. Under general, it's about proper documentation. Titling drawings, noting scale, cross-referencing correctly, using standard symbols, varying line weights so plans are clear, dark outlines for cabinets. Showing door swings with dashed lines.
Okay.
For notations, it's about absolute clarity. Describing special materials, features, clearances, alignments, calling out tops, spaces, toe kicks, backsplashes, noting shelves, brackets, sizes of standard cabinets, and dimensions. Precision is king. Dimensioning key heights, base cabinets, wall cabinets, the space between them, other clearances for appliances. Dimensioning miscellaneous stuff like grab bars, shelf spacing. It just hammers home how vital these precise drawings and checklists are for turning a design vision into something perfectly functional, perfectly fitted, without frustrating problems later. It's the difference between cabinets that slot in perfectly and ones that cause endless headaches and delays.
That's truly amazing. Shows how much planning goes into something we just use casually every day. Okay, moving upwards. Ceilings, often overlooked, right? Just blend into the background. But they're a huge part of how a space feels, how it functions. Our sources really highlight their importance.
They absolutely do. The ceiling plane, that overhead limit, it's one of the most significant parts of interior design. It takes up a huge chunk of the visible surface area, and it has to do a ton of jobs. Well, ceilings cover up the structure, the electrical wiring, mechanical stuff like ductwork, keeping it all hidden. They contribute hugely to the overall design concept, defining the space, influencing scale, giving character, setting the mood. Functionally, they're critical for controlling sound acoustics and providing light reflectance, which affects overall lighting and mood.
Right.
They also hold essential stuff: light fixtures, sprinkler heads, air vents, supply and return, speakers, smoke detectors, other electrical gear, and they can support suspended things too, like signs or curtains. Adds flexibility.
So not just a lid, it's like a multi-functional surface, almost the hidden brain of the room. How are they usually formed, and what are soffits and canopies?
Ceilings are basically formed by the underside of the floor or roof structure above. The ceiling material itself can be attached directly to that structure, gives a clean, often lower profile, or it can be suspended from it. Or, for that industrial look, you can just leave the structure exposed, make it part of the design. Soffits, or soffit ducts, are sections built down from the main ceiling, usually to hide ductwork or mechanical equipment, often around the edge of a room or above cabinets. Keeps the main ceiling area looking clean. Ceiling canopies and ceiling clouds are interesting design elements. Can be made of fabric, acoustic tile, metal, plastic. They let you drop the ceiling over smaller specific areas, even below another ceiling, usually suspended by wires. Often provide access to equipment above them while helping define zones in an open space.
So beyond the purely functional, there are different design approaches to ceilings. Sounds like they can really shape the mood.
Yes, several distinct concepts, each impacting the space differently. An exposed ceiling, the structure is the ceiling. Raw, industrial, modern, reveals the building's bones.
Right.
Direct attachment ceiling material fastened right to the structural frame. Clean, often lower profile, maximizes height. Then the very common suspended ceiling. Huge in commercial spaces.
Why suspend?
Well, in a room with a high ceiling, You can drop part or all of it to lower the scale, make it feel more intimate, or define an area. In commercial buildings, a suspended ceiling system, SCS, is often used to create a hidden space. The plenum.
The plenum.
Yeah, that gap between the suspended ceiling and the floor structure above. It's like the building's hidden service zone. All the ductwork, electrical conduit, plumbing lines run through there.
Yeah.
Keeps the visible space clean, but gives easy access for maintenance.
Ah, okay.
A typical SCS uses modular acoustic tiles supported by a metal grid hung from the structure above. The grid can be exposed with lay-in tiles or concealed using special edge tiles for a smoother look. Lights, air vents, sprinklers, speakers, all integrated into the grid. And importantly, the ceiling membrane itself can be fire-rated, protecting the structure above. In fact, beyond those, you can have combination ceilings using elements from different concepts. Our sources show visuals of closed ceiling concepts that are still dynamic, angled, curved, changes of material, drops. Shows a closed ceiling isn't always flat and boring. And of course, various open ceiling concepts that intentionally reveal the structure for a specific look.
And what about the actual methods for building these? What materials are common?
The construction methods line up with the materials and the look you want. Most common is probably gypsum board or fiber cement board on light metal frames, like drywall walls. Gives a smooth, continuous finish, clean, modern, easy to paint.
Okay.
For suspended ceilings, you often see ceiling tile on T-runners, usually modular acoustic board panels in a metal grid. Great for acoustic control and, crucially, easy access to that plenum space above for maintenance or changes. Plank ceilings use long, narrow panels, often wood or wood look. The source notes to observe the spacing of the framing, highlighting that the support structure is key visually and structurally for that linear look. And wooden slat ceilings, often with acoustic backing, used for aesthetics, warmth, texture, and for sound control, reducing echo, improving clarity. Each choice really impacts acoustics, lighting, and that overall feeling of spaciousness or intimacy in a room.
Okay, from walls, floors, ceilings, we now look skyward to the ultimate protector, the roof. First line of defense against everything.
Absolutely. The roof system is the primary sheltering element for the whole building interior. Its shape, its slope, have to work perfectly with the roofing material shingles, tiles, membrane to effectively shed rain and snow towards drains, gutters, downspouts.
Just shedding water.
Not just water.
Yep.
It also has to control moisture vapor movement, minimize air infiltration, regulate heat flow, solar radiation, and depending on codes and construction type, it might need to resist fire spread too. A roof isn't just the covering, it's the whole system covering and the structure supporting it.
And the types of roof systems, are they all flat or lots of variety?
Our sources cover various forms. Many roofs look flat, but almost always have a slight slope for drainage. Can't have water pooling up there. Main types of systems include the reinforced concrete roof slab. Solid, super durable, great fire resistance, structurally stable. Then there's structural steel roof framing. Can be things like steel rigid frames gives you big open spans without columns, like in warehouses or halls. More common for wide spans are steel trusses. These are lightweight, efficient frameworks, usually triangular shapes made of connected steel members, designed to carry loads efficiently over long distances. Like a series of triangles making strength from thin material, our sources show visuals of different truss types, each for different spans and loads.
Okay.
And finally, metal roof decking, corrugated metal sheets. They act as a structural diaphragm and often as the base for other roofing materials. Fast, efficient insulation.
Like any specialized field, roofs have their own complex language too. Understanding the terms helps appreciate the design that makes water go where it should, keeps the structure sound. Let's define some key ones.
Yeah, this is key to understanding roof geometry. The ridge is the highest horizontal line at the very top, where two sloping planes meet. A hip is the inclined projecting angle, where two adjacent sloping sides meet, sloping down from the ridge.
Okay.
A valley is the internal angle where two inclined roof surfaces meet, channeling rainwater down. A gable is that triangular wall section enclosing the end of a pitched roof, from ridge down to the eaves, often a defining feature. Dormers are those structures sticking out from a sloping roof, holding a vertical window or vent. Adds light, space, charm to an attic. The rake is the inclined edge of a sloping roof running from eave up to ridge. Different from the eave. A shed roof has just one single slope, like a lean-to.
Right.
The eave is the overhanging lower edge of the roof, extending past the wall, provides protection. And the sawset is the underside of that overhanging eave, often finished to protect the structure.
Those terms really paint a picture of how all those angles and planes fit together, functionally and aesthetically. And there's a surprising variety of actual roof shapes. Each must offer different benefits.
Oh, there's a huge architectural vocabulary in roof shapes.
Hmm.
Each form contributes massively to the building's style, its identity, often dictated by climate, local traditions, aesthetics. Our sources list tons of them. From the simple shed or lean-to, the common gable or pitch, the industrial sawtooth roof for light,
Right.
to the double gable, the multi-sloped hip roof, the complex hip and valley. Less common, but distinctive, are the geometric pyramid, the traditional barn-style gambrel, the graceful ogee, the multi-sloped mansard and its variations like the French or concave mansard, great for attic space. Then the dramatic ones, pointed conical roof or spire, the iconic dome, the inverted slopes of a butterfly roof designed to collect water. Each shape isn't just looks, it's an engineering choice, climate, materials, structure.
And speaking of engineering, what about the actual framing types holding these roofs up?
The sources mention the fundamental ways roofs are supported. Most common is rafter-type framing, various configurations of individual sloping timbers that directly support the roof deck. The visuals show how these rafters can be arranged differently to create the shape and provide strength. There's also a brief mention of light-gauge roof framing, modern method using thin, cold-formed steel members. Another option, lightweight, efficient. Each framing choice involves careful engineering to ensure the roof holds up, achieves the desired form, handles gravity, wind, snow.
Okay, we've journeyed through all the physical bits, from interior details right up to the roof. But how do professionals actually plan and budget these complex projects? Make sure it all lines up financially, not just structurally. Our sources introduce a critical system, like a universal language for construction costs.
Yeah, this is where the unseen organization really comes in, bringing order to potential financial chaos.
Hmm.
How costs are structured really depends on the project size. For small projects, condo units, small houses, budgets are often itemized, maybe how a contractor would bid it or how a designer presents it to a client. Simpler, direct breakdown.
Okay.
But for medium to large projects, budgets really should be formatted using the Construction Specification Institute's CSI index, better known as master format. This is the industry standard for organizing construction info. Crucial for clarity, precision.
Master format sounds like the Rosetta Stone for construction projects. What exactly is it? Why is it so important?
That's a great way to put it. Master format is basically the specification standard for the built environment. It's a huge master list of numbers and titles, classified mainly by work results. Imagine trying to build a skyscraper where everyone used different names for the same bolt, or organized instructions their own way.
Chaos.
Total chaos. Master format prevents that. It's a standardized numbering system, like a Dewey Decimal System for construction. Ensures everyone, architect, engineer, contractor, supplier, knows exactly what's being discussed, where to find its specific instructions, quality requirements, costs. Its main job is organizing project manuals, detailed cost info, and critically, linking drawing notes directly to the specs. Helps designers, estimators see where costs are concentrated by trade or material. It's a reliable way to develop and organize contract documents throughout the whole project.
So it brings consistency, clarity to these massive projects.
Exactly. Design, engineering, construction pros rely on it heavily to produce buildings that are safe, meet code, last long. Savvy owners use cost data organized by master format to check bids. It's truly influenced the whole industry, countless related standards globally.
What are the specific, tangible benefits of using master format for someone working on a big construction project? Why bother?
Oh, the benefits are huge, directly impacting efficiency and accuracy. First, consistency. Standard format means easier communication, sharing info between everyone involved. Everyone speaks the same language. Second, efficiency. Standardization means people find info quickly, saves massive time on complex projects, reduces costly errors that can ripple through the build. Third, clarity. Makes it easier to understand the exact scope of work for each part. Everyone's on the same page, fewer misunderstandings. And finally, compliance. Helps ensure documents and specs meet industry standards, regulations. Minimizes legal risks, safety issues, ensures the building lasts.
How is master format structured? Is it just one giant list, or is there a logic to it?
No, it has a clear logical hierarchy, easy to navigate. Highest level is the division, level 1. There are 50 divisions, numbered 00 to 49. Each covers a broad part of construction, concrete, metals, finishes, updated in 2020. Some are unused, allowing for future tech.
Okay, divisions. What's next?
Below divisions are sections, level 2. Each broad division is broken into multiple sections, covering more specific work within it. For example, Division 05 metal isn't just metal, it's It's got sections like O5 tennis and central metal framing, O5 200s and metal joists, O5 the 2D cedar zero metal decking.
Ah, getting more specific.
Yeah, exactly. Then sections get segmented into subsections. Level 3, even more specific. Take O5 thin as zero structural metal framing. That gets partitioned into things like O5 1200 structural steel framing, O5 1300 structural steel framing, O5 1300 structural steel framing, O5 1500 wire rope assemblies. Allows super precise categorization. Sometimes the specification number might even have 2 number decimals if a section needs even finer breakdowns. Absolute clarity down to tiny components.
That level of detail is incredible. And within each of those sections, how is the actual information organized? The stuff about the product, how to install it.
Within each master format spec, the details are consistently organized into a standard 3-part specification format. Predictable, consistent. Part O1 General includes the overarching stuff, related section numbers, required submittals like samples or drawings, reference standards, regulations, sets the context.
Okay.
Part O2 Product has all the details about the actual products. Manufacturing requirements, quality standards, finishes, material composition, tells you exactly what's approved.
Got it.
And Part O3 Execution includes all the requirements for installation or construction, preparation needed, the actual installation steps, quality control. This standard 3-part format means anyone looking at a spec, no matter their role, knows exactly where to find what they need, what it is, what it's made of, how it goes together. Master format truly is the Rosetta Stone of construction, ensures clarity, precision for huge, complex projects where millions of dollars, even lives, are at stake.
This is where the rubber meets the road, right? Where plans meet the budget. Our sources even give a peek into estimating concrete, a fundamental material. This isn't just guessing, is it?
Not at all. This is where precision directly equals cost and structural integrity. Estimating concrete means meticulously calculated material volumes based on very specific dimensions, exact mix designs, usually a Class A mix with a specific ratio of cement, sand, gravel for certain strength.
Why so meticulous?
Because a tiny miscalculation, say in the thickness of a slab over a large area, that can mean thousands of dollars in wasted material. Or worse, structural weakness. This precision isn't just about saving money, it's about building safely, responsibly. A small error here can cause huge problems later.
Right. Can you give an example from the sources? How does it work?
Yeah, let's look at the logic. For a footing, the volume calculation is simple. Length times width times thickness. Measure those, multiply, get the volume in cubic meters. Then, based on the Class A mix ratio, you know exactly how many bags of cement, how much sand, how much gravel you need for that volume. Same for a floor slab. Calculate by volume, or often by area. Know the floor area. Know the specified thickness. Multiply them to get the cubic meters needed. Then apply the mix ratio to get exact quantities of cement, sand, gravel.
And for columns and beams.
Same principle.
Got it.
Concrete collars, concrete beams. Measure their specific dimensions, height, width, depth, maybe diameter for round columns. Calculate the volume. Determine the material quantities based on the mix design. For concrete stairs, the source didn't give the final numbers, but the method involves accounting for riser height, tread run, stair width, number of steps, stringer thickness, all to figure out the total concrete volume needed.
These detailed calculations are absolutely fundamental then. Accurate budgeting, ordering the right amount of materials, preventing costly mistakes, delays. It's the numerical backbone, the hidden financial language that lets the structural and aesthetic vision actually happen within budget.
Indeed. It really is the numerical backbone of the whole process. Every cubic meter, every bag of cement counts.
We've journeyed through this really intricate world of interior detailing and construction, peeling back the layers of how our built environment actually comes to life. From that creative problem-solving and meticulous precision of detailing to the fundamental strength of walls, floors, ceilings, roofs, and the careful planning of doors, windows, cabinets. It's just abundantly clear that every single element is a testament to careful planning, precise calculation, expert execution.
And what we really hope you take away from this deep dive is that now, when you step into any space, your home, an office, a public building, you have a deeper, maybe more informed appreciation for the immense thought, the meticulous engineering, and those countless, often invisible decisions that went into making it.
Yeah.
You understand maybe why certain choices are made, how they profoundly impact how things work, how they look, even the overall cost of a project.
So the next time you open a door or walk across a room or just glance up at a ceiling, maybe consider not just how it looks right then, but that hidden network of calculations, specifications, chosen materials that are literally holding your world together. It makes you wonder what other invisible details in your daily life are quietly shaping your experience without you even realizing it, and what happens when those details are ignored.
Yeah, take a moment. Observe the details in your own home or public spaces you visit. Use some of the knowledge from today to spark some new curiosities. You might be really surprised by what you discover when you start looking at the world with a bit more understanding of its hidden construction and maybe the quiet brilliance behind it all.